Next, we're going to learn about titration curves. Titration is an analytical procedure that allows you to determine a concentration of an unknown by reacting it with a solution that has a known concentration. The solution with the known concentration is referred to as the standard solution. In order to perform a titration, you set up a burette, which contains your titrant that contains your known concentration, that would be your standard, and an Erlenmeyer flask below the burette, which contains your analyte or your substance that's an unknown concentration. Inside of your Erlenmeyer flask, you also have to add something known as an acid-base indicator. That acid-base indicator will allow you to know when the titration is finished by changing color. When completing a titration, we're interested in finding out the equivalence point, or when the moles of acid are exactly equal to the moles of base. We can't look at a titration and know when we're at the equivalence point, which is why we use an acid-base indicator to signify the end point. The end point of a titration is where you actually see the visible color change. When graphing a titration curve, you graph the pH of the unknown on the y-axis and the volume of the titrant that you're adding from the burette on the x-axis. The graph on the right shows a common pH titration curve. You can see it kind of has an S shape in this example. Some of the key points that we're going to want to learn about along the path of our titration curve are 1, before any titrant is added, 2, before the equivalence point is reached, 3, at the equivalence point, and 4, after the equivalence point. We'll go through all the math in depth and learn how to calculate the pH at all of those key locations on a titration curve. We're going to start off by looking at a strong acid being titrated with a strong base. On the left, we have a strong acid titrated with a strong base. You can see that initially the pH starts off very low before any base is added. All you have is strong acid in your Erlenmeyer flask. Slowly, you're going to start adding sodium hydroxide, a strong base, from the burette. Every drop of base that you add gets neutralized with some of the acid, and the pH will slowly start to rise until you reach a point where the pH is going to jump all the way up and become strongly basic. The equivalence point is the point at which the moles of acid are exactly equal to the moles of base. At a strong acid, strong base titration reaction, the pH at the equivalence point is exactly 7 because a neutral salt is formed. And the mirror image on the right-hand side represents a strong base being titrated with a strong acid. So in this case, your acid would be in the burette and your base would be in the Erlenmeyer flask. Initially, you have a very high pH because you're just starting with a strong base. Slowly, acid is dropped in and the pH starts to drop until it reaches 1 drop that's required and the pH will shoot all the way down, crossing through the equivalence point where moles of acid equal moles of base. Any additional acid is added is just adding extra strong acid, since all of the base has already been neutralized past the equivalence point. So the pH is low at the end. We're going to learn how to go through all the calculations for a strong acid, strong base type problem or strong base, strong acid type problem and figure out the pH along those key locations of a titration curve. Let's look at an example of a strong acid, strong base titration problem. Calculate the pH at the following locations for the titration of 40 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. The locations we're going to look at are before the addition of any titrant. In this example, the titrant would be the sodium hydroxide, which we're adding from the burette. 2, before the equivalence point. 3, at the equivalence point, where moles of acid are equal to the moles of base. And 4, after the equivalence point, where we would essentially be just adding excess sodium hydroxide. First, we're going to calculate the pH for this strong acid, strong base titration before the addition of any sodium hydroxide. Our overall reaction that's happening in our flask is our strong acid, HCl, plus our strong base, sodium hydroxide, reacting to form water and a salt. It's a neutralization reaction. So we'll form water and sodium chloride. Until all of the acid and base has completely neutralized each other, we're still going to have some amount of acid present along the way. So before we've added any titrant, all we have in our Erlenmeyer flask initially is just a solution of HCl. And we're told that we have a 0.1 molar HCl solution. HCl is a strong acid, so that means that it's present entirely as hydrogen ions and chloride anions swimming around. And with strong acids and strong bases, we can use stoichiometry in order to figure out the molarity of the hydrogen ions. If our molarity of hydrochloric acid is 0.1 molar, then the molarity of the hydrogen ion must also be 0.1 molar, and the molarity of the chloride ion must also be 0.1 molar. The fact that we have 40 milliliters of acid in our Erlenmeyer flask doesn't really matter yet because we just need to know what the concentration of that strong acid is. Recall that to calculate the pH, we need to know the negative log of the hydrogen ion concentration. And since this is a strong acid, the hydrogen ion concentration is exactly the same as the concentration of HCl. So to get the pH initially before any base is actually added, we're going to take the negative log of 0.1 molar. We should expect our pH to be very low. It's a strong acid and none of it has been neutralized. So the negative log of 0.1 molar comes out to 1. And it would be acidic because the pH is less than 7. Next, we want to calculate the pH somewhere before the equivalence point. We can choose how many milliliters of sodium hydroxide we're going to use for part number 2. Let's say that it's after 10 milliliters of NaOH has been added from our burette. So now we've essentially neutralized some of our strong acid with the 10 milliliters of base that we've added. At this point, this reaction is taking place with every drop of hydroxide that we add. Some of the hydrogen ion is being neutralized and we're forming water. In order to figure out what our pH is after we've added 10 milliliters of strong base, we need to figure out how many moles of acid we had initially and how many moles of base we added. Our moles of acid initially can be calculated by taking the molarity of the solution times the volume of the solution in liters. Our molarity of our hydrochloric acid was 0.1 moles of hydrogen ion per liter, and we were told that we had 40 milliliters of our strong acid in our flask. So we're going to multiply by 0.040 liters. That leaves us with our units in moles. Initially, before any base was added, we had 0.004 moles of acid in our flask. Next, we want to figure out how many moles of base we added. We're going to be before the equivalence point and we're only adding 10 moles of base, 10 milliliters of base. So to calculate our moles of hydroxide ion that we've added, we're going to take the molarity of our hydroxide, which is also 0.1 molar, so 0.1 moles of hydroxide ion per liter, times our volume in liters. 10 milliliters is equal to 0.010 liters. So when we multiply, that comes out to 0.001 moles of hydroxide ion that's been added after 10 milliliters. Now notice the moles of hydrogen ion is greater than the moles of hydroxide ion. That's telling us that there's going to be excess hydrogen ion left over because not all of it has been neutralized yet. The next step is to take the difference between the moles of our acid and the moles of our base that's been added. So we're going to take 0.004 moles minus 0.001 moles, and that tells us that there's 0.003 moles of hydrogen ion that is left over so far. That can essentially be neutralized still. Now that we have our moles of hydrogen ion, we need to calculate our concentration of hydrogen ion if we're going to figure out the pH. To calculate the concentration, we want to take the moles of our hydrogen that remains and divide by the total volume in liters. Initially, we had 40 milliliters of our acid, and we've added 10 milliliters of base so far. So we're going to have essentially 50 milliliters total in our Erlenmeyer flask at this point. So we're going to need to divide by 50 milliliters in liters which is 0.05 liters. Make sure that you account for the total volume of the acid and the base. So our concentration of hydrogen ion at this point comes out to being 0.06 molar. Lastly, to calculate the pH, we're going to take the negative log of the hydrogen ion concentration. So that'll be negative log of 0.06. And the pH at this point should be still pretty low. It comes out to a pH of 1.2, which is still acidic. We haven't neutralized all of our strong acid yet, so it makes sense that we'll get a low pH when we're going to be before the equivalence point on this titration. Next, we're going to calculate the pH at the equivalence point for a strong acid, strong base titration. Since our acid is 0.1 molar and our base is 0.1 molar, it would take us 40 milliliters of the sodium hydroxide to reach the equivalence point because we had 40 milliliters of our acid in our Erlenmeyer flask initially. That is only because both of them have the same concentration. Recall that at the equivalence point, that's where the moles of acid would be equal to the moles of base. We previously just calculated the moles of acid. Our moles of hydrogen ion were equal to our molarity, which was 0.1 moles per liter, times our volume in liters, which was 0.04 liters. That gave us initially 0.004 moles of our hydrogen ion. And it would take us 40 milliliters of sodium hydroxide to also get the same number of moles of hydroxide ion. So 0.1 moles per liter for hydroxide ion times 0.04 liters, or 40 milliliters, would also equal 0.004 moles of OH minus. In the last step, we had to subtract the moles of hydroxide from the moles of hydrogen ion. But now notice if you were to subtract those two, it would equal 0. Our pH is not 0 at the equivalence point. The pH is going to depend upon which salt is formed, if it's an acidic salt, a basic salt, or a neutral salt. So recall that our overall reaction was HCl plus NaOH forming H2O plus NaCl. At the equivalence point, we had the same number of moles of acid and base present, both 0.1 molar, both 40 milliliters were added. So those two are completely neutralized. There's no hydrochloric acid left, there's no sodium hydroxide left. At the equivalence point, all that's present is water and sodium chloride. So how we actually figure out the equivalence point pH is we want to look at that salt that's formed. We know water is neutral and has a pH of 7, but what about our sodium chloride salt? Sodium chloride is made up of the sodium cation and the chloride anion. We previously learned that the sodium ion is a group 1A metal and it is a neutral ion, and the chloride anion is the conjugate base of a strong acid and is also neutral. So since our salt we produced at the equivalence point from a strong acid, strong base is a neutral salt, the pH at this point will be exactly equal to 7, since all we have left is water and sodium chloride. No hydrolysis will take place for a strong acid, strong base titration, or for a strong base being titrated with a strong acid. You will always have a pH of 7 at the equivalence point in one of those two cases. Lastly, we want to calculate the pH after the equivalence point. So any volume after 40 milliliters of sodium hydroxide being added would be after the equivalence point. Let's say after 60 milliliters of sodium hydroxide have been added for our calculations. After we've reached the equivalence point, we're essentially just adding excess base to our flask. All of the hydrogen ion was neutralized once we reached the equivalence point. So now we're just running excess sodium hydroxide in there. We initially calculated that we had our moles of acid That came out to being 0.004 moles of our hydrogen ion. Once we've added 60 milliliters of sodium hydroxide, how many moles of base have we added total? So we're going to take our molarity of our base, 0.1 moles per liter, and multiply by the volume of base we've added in liters. So by 0.060 liters. So far, we've added 0.006 moles of hydroxide ion. Now when we take the difference and we subtract the moles of hydrogen ion from the moles of hydroxide ion, we're going to have excess hydroxide ion left over, excess base. So we'll take 0.006 moles of our hydroxide ion, subtract off 0.004 moles of our hydrogen ion, that's all neutralized, and what remains of our hydroxide ion is going to be 0.002 moles of OH minus. To calculate the pH, we should first figure out what the concentration of hydroxide ion is at this point. To calculate the concentration, we take the moles, 0.002 moles, and we divide by the total volume in our flask in liters. We initially had 40 milliliters of acid in there, and then we've added 60 milliliters of base. So we have a total now at this point of 100 milliliters in our Erlenmeyer flask. Make sure when you calculate the concentration that you convert your volume into liters, because that's what molarity is, moles per liter. So we're going to divide by 0.1 liters. Our concentration of hydroxide ion comes out to being 0.02 molar. Since we have hydroxide ion, it's probably easiest to first calculate the pOH by taking the negative log of the hydroxide ion concentration. So negative log of 0.02 molar gives us a hydroxide ion, or a pOH, of 1.7. And then we can use the relationship between pH, pOH, and pKw to solve for the pH, which will be equal to 14 minus the pOH. So we'll have 14 minus 1.7, or a pH of 12.3, once we've added 60 milliliters of base. And at this point, our pH is greater than 7, and so our solution is basic, as we would expect, past the equivalence point of a strong acid, strong base titration. So notice throughout all different parts of this example, when we were doing our problems, we were always using stoichiometry. We were looking at calculating moles and subtracting moles from one another, and we were able to use the fact that we had a strong acid and a strong base not to write any ice tables, or we didn't have to think about what X was, because we know with strong acids and strong bases that they're completely ionized in solution. So that makes this type of an example a little bit more straightforward than when we look at our next type of an example dealing with weak acids or weak base titrations.